Computation is not a ghost in the machine. While we often view logic as a pure symbol manipulation detached from reality, computability theory reveals a different truth. Physical constraints are not mere implementation details. They are the foundational determinants of what is mathematically possible. We begin by investigating how the spatial organization of memory dictates the temporal cost of knowledge itself.
Alan Turing did not model a machine of ethereal logic. He modeled a human clerk performing rote calculations. This created a physicalist epistemology where information is not globally available. In this model, the machine only experiences the symbol directly under its head. To know a global property, such as whether a sequence is sorted, the machine must actively travel through its environment, binding time to space.
The standard Turing machine is defined by sequential access. Unlike the random access machine model used in modern software, which assumes constant time access to any address, the Turing machine acknowledges the friction of distance. Accessing data is not a flat cost. It is determined by the distance from the current head position to the target cell. This transforms algorithmic design into a problem of topological path planning.
When a machine is restricted to a single tape, we encounter a sequential tyranny. Sorting, an operation that requires global comparisons, becomes a massive struggle against the limitations of one-dimensional space. On a single tape, even sophisticated algorithms like merge sort degrade to a complexity of O of n squared. The machine must constantly shuttle elements back and forth to make room for merged results or to compare distant values. Imagine a loom where the shuttle must travel the entire length of the fabric for every single stitch. This constant movement creates a massive temporal cost for even simple data reorganization.
The reason a single tape is so slow is mathematically anchored in the crossing sequence argument. To sort information, bits must cross physical boundaries on the tape. Because the head can only carry a finite amount of state information per crossing, the total time required is the sum of these crossings across the entire string. For a sort, this sum is proven to be at least omega of n squared, showing that the single head is a narrow bridge for information flow.
Breaking the one-tape limit changes the machine's topology. By adding independent heads, we liberate the algorithm from the constraints of a single linear path.
With 3 tapes, we reach the ideal merge scenario. Tapes 1 and 2 act as simultaneous input streams, while tape 3 captures the output. This setup bypasses the shuffling required on a single tape, allowing for a pure streaming algorithm. This architectural shift enables the machine to sort in n log n time, matching the theoretical efficiency of far more complex systems.
The jump from one tape to 2 provides a massive polynomial speedup, moving from quadratic to linearithmic time. While multi-tape machines do not expand the class of computable functions, they significantly improve efficiency. However, there is a catch. Any multi-tape machine can be simulated by a single-tape version, but that simulation incurs a quadratic slowdown, highlighting the intrinsic value of having multiple physical data paths.
When hardware resources are scarce, we turn to mathematics. The Polyphase Merge Sort is a brilliant example of resource minimization. By distributing data runs according to Fibonacci ratios, a 3-tape machine can emulate the efficiency of a 4-tape system. It allows for continuous merging without wasting time on redistribution passes, proving that clever algorithms can partially overcome physical hardware limitations.
These concepts are more relevant today than ever. While modern cache hierarchies are architectural tools to mitigate latency, they share deep conceptual roots with multi-tape simulation theorems, like the Hennie Stearns proof. Just as that theorem uses nested zones to minimize traversal overhead, our L1, L2, and L3 caches organize data to ensure that frequently accessed information is physically closer to the processing core. In the universe of computation, there is no action at a distance. To organize the world, you must traverse it. The Turing machine remains a vital map of the physical costs of thinking, grounding the ephemeral nature of software in the hard reality of physics and space.